Hello. Today's project was getting my Annunciator Zero MIDI to work and then starting to interface to an Arduino using David Schmenk's Arduino library and his Plasma utilities for writing and reading SD card images. So I ran into some snags along the way. Well, let's take a look at the Arduino. This is first the Annunciator MIDI out. So this red light is now on. That's Annunciator 0. And we're loading a music. Okay, and we're playing it on a Yamaha Easy guitar. Okay, and it has the display of the notes. Okay, I'm going to stop the music. Okay, so what's going on is if we look at the side of the Apple IIe, you see a black wire and you see two wires coming out of those slots. So those are wires going into the game socket, and then they go up here onto the board. So at the bottom of the board is the lowest one is the C040 strobe. Then the white and the black are the two annunciators that I need. And then all the rest of my signals are coming from the back panel game port. So there's a little cable back there that comes out, and then I have labels of what the pins are doing here. So I have these 8 signals and the green for ground. So that's what these two cables are. So I need to do an SPI interface to the Arduino, and that's what this ribbon cable is. So there are 4 pins. So following David's specs, this little card shows what I'm doing: the MISO, the MOSI, the SS, and the SCK. So that C040 strobe, I believe, is my problem, because I'm currently not, when I do a directory of the SD card, I'm not getting anything, even though there are files on it. Okay, so the MIDI is going up here, so that red wire is taking the Annunciator 0 output up into the 7404 chip and doing two NOT gates. And then that resistor is taking it out to pin 5, which goes into the MIDI cable. That little MIDI cable is down here, the little coupler into the MIDI cable, into the guitar, the MIDI input. So this little guitar can do, it has LEDs, and I've been working on a little program that does sysx messages to turn on the LEDs. So that's a MIDI spec with two 220 ohm resistors. It's a current loop going between pins 5 and 4 on the MIDI cable. So you're inverting, and taking that output. So you need +5 and ground. So it's a simple circuit. So I already had it on that breadboard, and I just attached the 2 breadboards together. So now I want to get this working, and I'll be debugging as I go. Okay, so now this is the MIDI driver program for the Annunciator MIDI interface. So this is machine language at 9000, and these are the entry points. So 9008 is the one that I call from AppleSoft to send a bunch of bytes out the MIDI interface. So just walking through this, the Annunciator addresses are defined here. There's an on and off for each of them. And then there are some 0-page locations, the number of bytes to be transmitted, and a pointer to the bytes. Okay. And then these are the entry points, the main entry point, initializing. And then this source code is available on my website. And so to transmit a byte, I am bringing it into the accumulator and jumping to a subroutine called transmit1. So here I am getting the bits out of that byte, shifting the accumulator left, transferring it to X, and zeroing it out and doing an add with carry, and I'm storing them into the bits. So I'm actually self-modifying the code below it. And this is where I change it to bit the correct annunciators, whether they're the on or the off, in a tight loop, timed to based on the 1 megahertz clock, to give the precise start and stop bit times required by MIDI. Well, there's a start bit, and then there's 8 data bytes, and then a stop bit. And there's a 22 cycle delay right there. That's a subroutine. And then some test messages to get the program tested and to turn all notes off. So the test messages are reading this data, which the first one is a note on for a C major chord. The 3C is a C, the 40 is an E, and the 43 is a G. And then that's the note off. So to test it, you would use those entry points to turn the note on and off. And if you hear the note, the chord, that means your board is wired correctly and the Apple is communicating out to the annunciators. And then this quiet message is a whole bunch of data bytes to turn off every channel. This looks like the all sounds off, all notes off. So you look at your MIDI spec and you'll see the controllers. Okay, this video I want to do a deeper dive into this MIDI file format 0 device driver for the Annunciator MIDI that you could build on your game I/O socket on an Apple IIe or earlier. So if you break out of this with Control-C and do a catalog, so you download this disk image from my website, and on this site, what you want to do is look at MIDI driver.object, which is at address 9000. Deload MIDI driver. Okay. Okay, so now if I do a 9000 list, okay, so there are a few entry points. If you look at 9008, that's what we're going to call from AppleSoft. And if you look at 9000B, E, and 11, those are test routines. So if you look at 90FA, so here we are looking at data at 9118 and 9118. Okay. That is a control change event. So I want to look at something else. Let's look at the 90 EA and DA. Okay, 90 DA. Okay, so we are looking at 910A. So you see the store STAs in CE and CF, that's the address, and then the number of bytes is in D7. So the 7 bytes. Okay, so what we want to do is look at 910A, and then that 90EA entry point is at 9111. Okay, another 7 bytes. So if we look at 910A, 9120. So there's your 93C40. So those of you who know MIDI, 90 is a note on for channel 0 of a MIDI instrument. Then 3C is the note number. So if you multiply that out, 3 times 16 is 48, and C is 12. 3 Charlie. Okay, so 48 and 12 is 60, and note number 60 in the MIDI spec is a middle C on a piano. And 40 is the number 64, and that's a volume. So volume, it's velocity. It's really how hard you hit the piano key. So this 64 is the middle. It's like half of the range, half of the volume. If it was 7F or 127, then that is the full volume or full velocity that you're really pounding on that key. Okay, so it's going to play the note 3C40, and then there is no byte with a high bit set after that, so it's called running status. So the 90 status byte still applies to the 4040. So 40 is the number 64. And if you count up from C is 60, C sharp D, D sharp E is 64. So you're playing an E. And then there's a 40 and a 43. Okay, 4340. So the 43 is a G, because then you go E plus 3. So E plus 1 is an F, plus 2 is an F sharp, plus 3 is a G. Okay, and we're only playing 7 bytes. So we're playing up through that 9110. And then if you look at 9111, those 7 bytes are the same notes, but the velocity of 0. So that is going to turn the notes off. So I'm going to turn on my MIDI guitar. Okay, and put it up here. Oh. That is not MIDI. That is an alarm clock waking me up. Okay, so to test this, you have to have a MIDI cable that comes out of your home-built interface, and I suggest use like a MIDI coupler to connect it to a MIDI cable to a real instrument. And what we're going to do is now test the program. So looking at the entry points here, we're going to do a 900E. Okay, the reason we didn't hear anything is we didn't do the 9000 initialization routine, because it has to turn on Annunciator 0. So just looking at that. Okay, that's nice. You're just turning on Annunciator 0. If you had an LED connected, you would see that LED go on. So let's try it again. Okay. Okay, you heard a C major chord. And now I'm going to try 90DAG, N, 90EAG. Okay, so you heard that was a very short MIDI. So what is great about this is from Applesoft, you can poke these values. Okay, so before I show you how to call this from Applesoft, I want to look at the routine at 9008. So it's jumping to 901B. So it is loading D7, which has the number of bytes, storing it, and it is getting an index into the address that you pass in at CE and CF, and it's JSRing to 9034 as a subroutine, and then it's going to get each byte, byte 0, then increment Y, decrement D7, and check if your D7 is 0. If it's not 0, it goes to 9022. So it's going to go through however many bytes, up to 255 bytes, and JSR 9034 to send the bytes out. Okay, so we've walked through this in the assembly language version before. So if you look at 9034, it is doing some shifting. So at 903A, you have arithmetic shift left. It's shifting the bits left. And it is self-modifying the code at 90C5, 90BF, 90B9. And then it's going to send the byte out. So it's going to send MIDI bytes out with the stop bits and start bits. So here's a simple program for testing it. So to explain what I'm doing, you could choose any location in memory that's free. So I'm using hex 300 or 768. So at 768, I'm putting the 90, which is the note on command, and then 769, I'm poking the note number, and I chose 72, because if middle C is 60, you add 12 to go up an octave, so this is the C, an octave above middle C, and then at 770 is the velocity. So 127 is the velocity that I want, the full volume. Then line 20, I'm poking D7. So that's the number of bytes that I want to send out through MIDI with the number 3. Okay, so that's 3 bytes, and then line 30, I'm poking the address of my data. So CE has a 0 and CF has a 3. So if you take the CF first and then the CE, that's 300 hex, or 768. And then I am calling the routine to send out the MIDI bytes. So I run it, and you hear that middle C. That's the octave above middle C. So this is a great way to get kids building something, learning about a device driver, and testing it with AppleSoft. Okay, now this is an AppleSoft program that is going to control the lights on the frets of the MIDI guitar. So let me just walk you through it. So all that you have to do to initialize is run the MIDI driver, and that will run that routine at 9000 to initialize the Annunciator 0. It'll turn it on. Then I'm skipping over the 3, 4, 5, and 6 because those are subroutines. So to make your AppleSoft faster, you put small subroutines at the beginning of your program. Okay, so then at 10, my address is 768, that's 300 hex, and I'm poking sysx messages. So those are system-exclusive messages that manufacturers create to control elements of their hardware. So like for Yamaha, for this guitar, they have system-exclusive messages that are interpreted by the software in the guitar to turn on and off the frets on the first 6 frets of the guitar. And that's used to teach people how to finger chords. Okay, so then at 20, I am reading data, which you'll see later in the program, and I'm poking it at the address. So there are 9 bytes of data that I'm poking, address plus 0 to address plus 8. Okay, so my message is 9 bytes long, so on line 30, I'm poking the length of it as 9, and on line 40, I'm poking the address as 300, and then on line 50, I'm calling go sub 3, which is calling the 9008 entry point, which is the MIDI driver, which will send the MIDI out based on the data that you've poked into memory. And then the remaining lines, I'm actually calculating what I want to change in the data. So in the 100, I'm saying my string number is 2, and my fret MIDI note is 4 times 16 plus 13. So that's 64 plus 13, whatever note that is. And that is what I'm going to play, go sub 5, which is going to... Okay, so 5 and 6, the system exclusive message, it needs a string and a fret number. And if you look at the difference between 5 and 6, on 5 we're poking 768 plus 5 with a 3, and 6 is a 4. So 3 turns the note on, and 4 turns the note off. It turns the light, the LED on or off. Okay, so I'm go subbing 5 because right now there's nothing showing on my guitar, and I want to turn everything on. Okay, so I just figured out all that. And then 1000 is the data for the system exclusive message if you look at the manufacturer's spec. Okay, and all I do is type run, and the lights come on. So imagine what you could do with a program like this. You could show chord patterns on the guitar and play notes. And now what this is also illustrating is that MIDI can be used to control lighting and other devices. And if you do some research into how shows are put together, there is a spec called MIDI show control. So this can get a child very interested in computer technology and music, and it's a really integrated learning experience. So I encourage anybody interested to take this code and run wild with it. So one of the snags I ran into when I was wiring up and it didn't play the music initially was this. See, I'm not using the +5 volt or the ground on this board, even though I probably should. And then I wasn't actually getting power into the chip. I think I was assuming that one of these wires was using I think that red one was probably plugged into this, and it was assuming something that I shouldn't have assumed. So it's a little lesson there. And my suspect for this problem here is the strobe input. I want to see if I can write a test program that I can run from the Apple to send signals to the Arduino and then put an LED on it to see the results. So like a simple sketch on the Arduino, like if the MISO is 1, or whatever, MOSI or MISO, I'll figure it out, then turn on this LED on this pin. Otherwise, and when I get the strobe, I'll be in a tight loop looking for when the strobe changes, and like for each change, like from low to high, I would then toggle an LED. So that's what I'm going to work on. Okay, this is an Arduino sketch that's testing the strobe output from the Apple, the C040 output. So what I have here is showing that it is normally high, but it goes low for a half of a microsecond. And what I'm going to do is connect this wire to pin 6 on the Arduino. And, okay. Now, let's see. It stopped running. We're still high. Oh, yeah, now we are high. Okay. So it is not detecting a low strobe anymore. Okay, but now I'm going to type C040. Okay, so that number is 237443364. All right, so that's a peak, and it looks like it did it. I'm going to type it again. If it detects the pulse. Okay, hitting enter. 344, so it's hit and miss, it seems. Like I could type it 10 times and see how many times. So 1, nope. 2, 3. All right, so if I do C040.C04F, any number in those range should trigger something. Okay, so it triggered it twice from that sequence of pulses. So I believe that could be an issue if the Arduino is not able to keep up with these pulses. All right, let's try it one more time. C040 to C04F. Okay, so we got 2 out of 16, it looks like, that it caught on the half microsecond. All right, now let's take a look at this short program that I hacked in there. So just loading it and then a delay loop. So let's see. Yeah, for 256 pulses with a 256 delay in between pulses. And let's see what happens when I type 300G. Okay, I'm hitting enter. 776 is the last one. Okay, so we got a few of them. So where's that? 776 is at the top here. And we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In that series of bursts of pulses. So this shows the types of communication issues you could run into, where you're not keeping up or you're behind. And here's the sketch. I am just checking pin 6 and checking pin mode to input, and using my serial monitor to see the output. I'm digitally reading it and checking if it's equal to 0. Then I print the low message, and I write the timestamp. Otherwise, I don't print anything. I stay in this loop while it's high. Alright, so now if I run it serial monitor again, there's no output, and I'm going to type 300G, and now I get my output of a series of pulses that it caught. Alright, one more time. And it looks like it's asymmetric. Alright, so the next thing I need to debug is the paddle button 0, and I found a reason for it. There's an Apple technical note, number 9, for the Apple IIe that explains the difference. So who would ever think you'd be reading Apple IIe technical notes on an iPad in 2017? But this explains certain critical changes to the hardware of the Apple IIe, the newest Platinum motherboard. Okay, in order to debug my wiring, what I did was, for the Arduino, I wrote a sketch that displays several variables. The current time, and the next time is calculated a second from. I want to create a pulse of every 1 second, and the output of that pulse is going on the paddle button 0. So you see that flipping from 0 to 1, back to 0 every second. And what I'm showing here is that this pin 7 on the Arduino, that white wire, is going into an LED to ground, so every second the pulse is being generated. So that is correct in the logic. However, I'm having problems getting it onto the Apple. So, like, as a test here, I'm going to take this off and put it on this yellow wire, which is the game controller input for pin. Okay, so the first thing I'm going to do is prove that if I connect that to +5 volts, that the number here will change. So here I do get a 1. So yeah, so I disconnect, I reconnect. So if it's going directly to +5 volts into the paddle button input, then yeah, so just trying to do it one more time. Yep, then you get a 1. Okay, so that's checking the high bit of C061. But now I'm taking the logic out of the Arduino pin 7, which we saw works with an LED. So here, put this wire in pin 7, and then connect it to the yellow wire here. Oops. Okay, wiring on the fly. Yellow wire here, pin 7. See, this is the great thing about the Apple IIe. You could put wires all over the place. You don't have to be so careful. You're not going to really mess things up. But see, I'm getting a 0 every time. Now if I press the Open Apple key, I get a 1. So yeah, so you see the program's doing that, but that pin 7 from the Arduino is really not giving enough current into that paddle button input. So what I'm thinking I may have to do is run that through 2 inverters, and then take the output of that to the push button input. So I previously debugged that my Annunciators are working, so that I tested using this sketch here. So it always makes sense to do a test sketch to make sure your wiring is correct. Just walking through what that is. I have my pins. I'm setting them to input for the 3 input pins, and the output pin is the MISO. And I'm digitally writing a low to that, and then I open my serial port at 9600 baud for text. And then in my loop, I'm digitally reading the 3 pins, and I am checking the time, the microseconds command for the time. That's our current time. The next time I calculate initially as the microseconds plus 1,000,000 microseconds. And so I print everything out, and then for toggling the time, if my current time is greater than the next second's time, then I'm going to toggle. So I check it. Is my toggle 0? If yes, I'm going to set it to 1 and write a high on the MISO pin. Otherwise, I'm going to write a low and set toggle to 0. And in either case, my next second is calculated again at that time whenever we overflow the next second's time. And that's in the loop for the Arduino. Okay. And then this AppleSoft monitor is a simple peak statement. So have fun debugging. Okay, this is another reason why the TSA will pull me over when I go to Kansas City, Missouri.